All right, hey folks, welcome back to another episode in the Advent of Code 2023 series, wrapping up towards day 18, which was the last that I did, but today we're on day 17. Today's problem is called Clumsy Crucible, and the crux of this problem is we're given a map, and we have to move from the top left to the bottom right, and as we move along through this map, which is represented by this 2D array of integers, we collect heat, and the amount of heat that we collect is dependent on what cell that we're in, and we want to get to the bottom corner collecting as little heat as possible. Now there are two additional rules. We can keep going in the same direction that we're facing. We've got like a little cart that we're pushing along for up to 3 blocks in a row, or we can turn left, or we can turn right. So it's a little bit of a pathfinding algorithm with some additional complexity, making our way from the top to the bottom. Here's a slightly annotated version of the previous example, where you can see in each of the cells that now doesn't have a number in it, the move that we took to get to that spot. In this particular example, straight off the problem description, the total heat for this path is 102 units. So going from the top there down to the bottom. Now let's have a look at how we solve this in the code. Number one, we've got an enum here for direction. Nothing too complex here, just have 4 different directions we can travel in. We have a structure for each of the positions that we've visited, or potential positions to visit, I should say, called head. Again, we're using position, row, column, direction, one of those 4 directions from before, the chain, which is how many steps we've taken in the current direction, and heat, which is the total amount of accumulated heat. We implement 2 traits for this head to allow sorting, so order and partial ordering, and this just allows us to sort a collection of these head structures based on the heat within them, and you'll see why that's useful in a minute. A couple other structures that we use throughout the solution here. We look at key, which is very similar to head, but it doesn't store the heat. And we use this as a unique index in some hash map type structures. And we have map, which is just our representation in memory of the input file. Couple of little helper functions here, which is left and right, and it takes a current direction and tells us what the next direction will be if we turn to the left or the right. This just cleans up the code a little bit. We then also have a function called valid directions, which given a current position, direction and length of chain, tells us what we could possibly do next. So what this looks at is, hey, have we been traveling for less than 3 steps in the current direction? If so, we can keep moving forward, and we can always move left and right. And then it returns that list for us to process later. After that, we have a move in direction function, which takes a current position, a direction, and the size of the map. It either returns a new position or it returns none if we've moved out of bounds. So this just allows us to quickly test a step in a given direction. The most activity of this problem happens in this run sim or run simulation function. It takes an initial position, initial direction, and a map, and returns a result, which is the total amount of accumulated heat throughout. Now we store the head, which is the collection of all candidate new positions to test, in a binary heap. The reason we do this is that it becomes sorted with the minimum at the top, and you remember we implemented those 2 traits, which means that the minimum will be the lowest heat, and the pathfinding algorithm that we're looking at works when the potential candidates are sorted in order, and this gives us an automatic way to do that without worrying about calling sort every which position in the function. We store a hash map of keys and heat, or I32s for the heat, which is what we call distances here. Traditional pathfinding is about the distance from A to B. We have distance here, but it's accumulating heat along the way. So we store that in a hash map. And then we keep a set of all of the places that we've been before so that we don't double up and revisit potential positions. Now, notably, the key here is not only the position, but the direction and the length of the chain that we've had previously getting up to that point. So you can revisit a position if you're facing a different direction or if you're at a different stage in that 0, 1, 2, 3 maximum length. So we initially populate the binary heap with initial position, initial direction, no chain, no heat. And we say that also the distances map at that position has a maximum heat of 0 because that's our starting position. Continuing through this function, we continue until we've run out of candidate places to check. We pop one off the binary heap. We create a new key based on the current position, direction, and chain length. We do a little debug print here just to see where we're up to, but you can ignore that mostly. If we visited this spot before, we just skip it. We don't reprocess this potential position. And the reason we can do that is because we have sorted the collection. We know that the one up the top will be the smallest one, so we'll always reach that destination first. We take note of the current heat, and we get a list via our valid directions function of where we might potentially move to next. Further down, we attempt to move in those directions. Now that could be forward, left, or right as a collection of 3 different candidate directions. We update our position if that position is still within the map. So we've got some rather than none here. We get the new heat value. We check that we are, if we've started moving in this direction, we extend the chain. And then otherwise we compare the heat in this spot to the current best heat in that spot. And if we found a new shortest heat way to get there, we store it. And if we do that, then we put this new position in the candidate list and we update the distances collection to reflect the new heat. We also mark this node, well, after we've gone through all the candidate future directions, we mark the original position as visited and we continue throughout. So this is a pretty standard pathfinding algorithm, just with those little tweaks to account for the special rules about how we can move as a unit and the heat that we have to accumulate along the way. Cool. So finally, the day 17, we pass the input file, we read all of the input into our map structure and pass it into our simulation, and then we'll get our final result printed along the way. So that's all for part 1. There are a couple of small changes for part 2, which we'll go into right now. So part 2 changes the rules of movement very slightly. It says if you start moving in a direction, you must move at least 4 steps in that direction. And as a, counter to that, you can now move up to 10 steps in a given direction. So to make this work, we only have to make 2 changes to our code. One in the valid directions function. So we return forward as a valid direction now all the way up to 10 strides. And we only return left and right as valid directions if our current chain is greater than or equal to 4 steps in length. The other thing we do is back here in our run simulation function, we only update the distances array. You can see here on line 18, if the current chain is greater than or equal to 4, because those first 3 steps in that direction, we can't stop there and change our mind. So we really just ignore them and continue on our way moving in that given direction. And with that, that gives us the updates that are required for part 2. You can find the actual code for this in the repository linked below if you want to run this yourself and get the answers. But with that, we're done. This is a nice, short, sharp one. Hope this has been interesting. As always, I'm Elliot. I build stuff, and I'll catch you in the next one.